Building a quantum ready workforce. I'm Tonya Hall, and joining me is Dr. Abe Asfaw, Global Lead for Quantum Education at IBM Q. Welcome, Abe.
Hi, Tanya. How are you?
I am good. Thank you for joining us. Give us a brief summary of your personal journey into quantum computing and education at IBM.
Well, let me start off by telling you that I was a very indecisive undergraduate. I really liked mathematics, physics, computer science, and a professor who saw this sort of eagerness to study anything and everything related to these things gave me a book called the Feynman's Lectures on Computation, which sort of laid out the thesis for why quantum computing would be something useful. And as a result of that, I pursued quantum computing in graduate school. And in 2016, when I was working on making small chips that are used for quantum computing, I remember hearing the news that IBM became the first company to put a quantum computer on the cloud. So this changed the field dramatically from a field where you needed access to a lab to a field where anyone from anywhere in the world, just over the internet, can access a quantum computer. So now this field became something that anyone can participate in and contribute new, fresh ideas. So that's sort of my journey so far. And realizing this, I joined IBM to make sure that everyone in the world knows about quantum computing and also knows how to program quantum computers.
Probably the first question to address regarding quantum education is what kind of problems are quantum computers best suited to solve today? And how do we know when quantum is the right tool for the job?
Right. So I should point out that there are several companies that are working with IBM as part of the IBM Q network to explore exactly this problem. So there are problems where we know quantum computers can provide speed up. There are some celebrated algorithms, for example, Shor's algorithm, which allows us to factor large numbers that are products of prime numbers, finding those factors. So, and on another algorithm called Grover's algorithm, which allows us to get quadratic speed up in search problems. Outside of these problems, which are kind of going to be available in the future because we don't have the technology to use those algorithms yet, the industry is exploring specific applications like optimization problems or simulating chemistry problems using quantum computers. So anytime those kinds of problems are applicable in your industry, it's a good idea to explore whether or not quantum computers can provide some sort of advantage.
For someone who's already adept at developing applications for classical computers, what is the first difference they'll encounter when learning to develop for quantum?
Right. So that's a very good question. This is an entirely new paradigm of computing. So you're not programming with bits anymore, programming with zeros and ones, but really you're programming with quantum bits, which can take on quantum states at this point. So the kinds of features that you take advantage of are no longer familiar. So just to give you an example, if I had to search through a number using a classical computer, the kind of work that I would do would be going through the list of numbers and saying yes or no. So turning something on or off. So the logic that I'm building is based on and off logic, and we're switching transistors on and off to do this kind of computation. The kind of effects that you're taking advantage of in quantum mechanics is one, uh, the ability to have superpositions of states. So not just zeros and ones, but also states like equal superposition of 0 and 1. And also to take advantage of another feature of quantum mechanics called entanglement, which allows you to have these quantum states between two quantum bits that are correlated once you measure them. So entirely new features become available to you. And it's these features that make the computation more powerful than the classical computation that we have today. So a classical developer today would need to adapt to these new features that become available to them.
There seems to be a mismatch between the number of quantum machines ready to tackle challenges and the supply of qualified engineers and researchers who understand the tools. So, what's the story behind that?
Right. So this is so going back to this idea of new quantum mechanical features that become available to you, there really is the need to develop a workforce that has this sort of quantum readiness, the ability to see a problem that we have somewhere in industry today and translate that problem into something that a quantum computer can solve. And this mismatch between the kinds of developers that we need and the kind of work that should be done in the field exploring quantum computers is the reason why there's a need to sort of educate new round of developers. And that's why I'm so excited to do the work that I'm doing today, which is focusing on educating people so that we build a workforce based on these principles.
Can you get a university degree in quantum computing yet?
Yes, you can. With and I'm since 2016, it's been possible for you to not just get a university degree in quantum mechanics, but also learn how to program a quantum computer because they're available on the cloud. Uh, you can get a university degree, but what you'll find is that most of the people working in the field are coming at the PhD level. And the goal here is to really lower the barrier of entry to undergraduates. The idea here is an undergraduate who comes with some familiarity with linear algebra, so maybe sophomores in college, can easily get exposed to quantum programming. And to make this possible, what we're trying to do is supplement the university courses and the textbooks that are available with textbooks that show students how to program quantum computers. So part of my work has been making available an open source quantum computing textbook that students can use as they're learning. And at the end, what we'd like to see is undergraduates being able to join the workforce and really start to explore these quantum applications in industry.
In relationship to making this education more accessible, tell us about the quantum education tools that and resources that IBM offers and how much they cost.
Right. So, first of all, free is a number I want you to remember. So, everything is available for free. If you go to community.qiskit.org slash education. So, Qiskit is the name of the open source software that programs our quantum computers. Uh, if you go to community.qiskit.org/education, you'll see this gallery of a video series that shows you how to develop quantum computers. So you can have videos open on one side of your screen while you're programming quantum computers on the other side. We also have a textbook that you can take a look at, which you can use to supplement traditional quantum algorithms textbooks. I actually have the textbook open and I'm ready to show you a brief snippet of it if you'd like.
Okay, let's do it.
Yeah, so right behind me, you should be seeing a screen which looks like an outline, which is roughly the table of contents for the textbook that we've put together. And the idea here is we really try to go through the prerequisites that the undergraduate that I mentioned to you needs to cover before they go into the details of quantum programming. And once we go through their prerequisites, we really have a range of chapters here that show students how to do traditional quantum programming algorithms and also to really explore some applications that are interesting for today's quantum computers. We also have a section here that allows students to really go into detail measuring the properties of quantum computers today. So this is the kind of thing that you would only have been able to do with lab access just 3 years ago. But now you can just follow this textbook and learn how qubits are made, what kinds of properties they have just from an internet connection, which to me is fascinating.
Great resources, Abe. And I think the idea of to your point, making it more accessible to a larger audience makes sense. I want to follow up with this though and ask from this United States standpoint, where we are in this leadership in leading this area of technology, how does the U.S. compare to quantum capable countries in educating their engineers and researchers?
So I can't speak to the specifics of the any country outside of the US because the US is the one that I'm most familiar with. But I can tell you certainly that the concentration of researchers and the concentration of work that is coming out of the US is really in the cutting edge. Just looking through every day, if I browse through publications in this field, it's dominated by US researchers, and this leadership is very clear looking through the literature.
That's good to hear. Well, I'm glad that you're leading this, that you're at IBM. Dr. Abraham Abe, Asfaw Global Lead for Quantum Education at IBM Q. If somebody maybe wants to, I know you gave this earlier, but if somebody wants to get their hands on these tools, or maybe they want to connect with you personally, Abe, how can they do that?
So, Tonya, if anyone wants to get access to our educational tools, the link that I mentioned earlier was community.qiskit.org/education. Anyone can go to IBM's quantum computers and program them. They can do so by going to quantum-computing.ibm.com. And for me personally, you can find me on Qiskit's Slack channel by going to qiskit.slack.com, and also on Twitter. I'm at Abe_Asfaw.
Perfect. Well, I'll find you on Twitter for sure. Thanks again. Thanks again, Abe, for joining us. And if you guys want to find more of my interviews, you can do that right here or go to tonyahall.net. Thanks for watching.